Okay, so tonight, before I introduce Dr. González, I want to say gravitational waves is one of the most amazing things that's happened in physics and astronomy since I've been in this field. I mean, to think about the fact that here's a wave, a phenomenon that comes about that it doesn't affect us in any way that we could have guessed. It comes from the theory, and yet in our lifetimes and in the last few years, it's been proven to be real. So part of it is sort of the amazing fact that there was this thing that we never imagined, and now we are experiencing, now we are measuring them and using them. And the other thing is that the technology in order to do this is equally amazing. So I'm sure that Gabby's going to say a little bit about the precision that the Gravitational Wave Observatory LIGO is able to achieve. But when you hear the numbers, it's like many numbers in astronomy. You just can't relate to them. It just seems so amazing that they could do this. So we have a really great speaker tonight because she has been involved in what has happened in gravitational wave astronomy over the last few years. Dr. Gabriela González grew up in Cordoba, Argentina. She did her undergraduate work there. She then went to Syracuse University for her PhD. She worked after that at MIT and Penn State, and she's now at Louisiana State University, which is right next to one of the LIGO gravitational wave observatories. And she was, for 6 years, the spokesperson for the LIGO science collaboration. Spokesperson is the title of the person who leads the science collaboration. So she was organizing and coordinating, which for scientists is a challenge, the group of people who were working with the LIGO data and trying to understand it. So I will hand off to Dr. González to talk about Einstein, gravitational waves, black holes, and other matters.
Thank you. Well, first of all, let me thank Todd and Yair and all the people who I have been talking to here at the Las Cumbres Observatory and at UCSB. It's been great. I have been in Santa Barbara several times, but probably not in the last 10 years or so. So it's great to be back. And like he said, I want to tell you about a lot of things. This is a very long story, and I will try to condense it in 45, 50 minutes, but I might run a bit longer. Not as long as this story. This story started more than 1 billion years ago. There were 2 big black holes, each one about 30 times the mass of the sun, but very compact. These were black holes, and they were, being from Argentina, I like to say that they were dancing a tango, orbiting around each other, and getting closer and closer together until they embraced each other and formed a single larger black hole. And that dance produced ripples in space-time that have been traveling across the universe since then. That was 1 billion years ago. On Earth, only the multicellular organisms were just getting organized. Now, fast forward, I'm not going to go through every one of those billion years, but now 100 years ago, after humans evolved in Earth and Newton created his theory of gravity, there was Einstein who developed another theory of gravity. And he did this because he had created this theory of special relativity that made a lot of sense of electricity and magnetism, and it came up, that theory involved a universal speed limit, and that's the speed of light. The speed of light, he said, and it was proved by experiment, was constant in every frame of reference, and nothing traveled faster than the speed of light. But Newtonian gravity was instantaneous. The theory that we learn in school about how the sun attracts the Earth and that makes the Earth go around the sun says that if the sun happens to disappear in a Gedanken experiment, like Einstein liked to think about, then the Earth would know that right away, instantaneously, and then would keep going straight instead of going around the sun. So that was faster than the speed of light. So he developed over the years and published in 1915 a different theory of gravity, which is beautiful, but very, very complicated. So I'm not going to put the formulas. Even in graduate school, it's a pain to learn this theory. But the concept is that masses, all of us, everything in the universe, lives in a space-time. Space-time I like to imagine as a three-dimensional grid. That's a space. That's how we measure distances. And if the grid is like you imagine it, then all the distances between the corners are all the same. And time, I imagine like a little clock in every corner. And then the way we like to do physics, even in college, is thinking that all these clocks are synchronized, all these distances are the same, and that's how we measure space and time. What Einstein theory said is that if you have a mass living in that space-time, that deforms the grid. The distances are going to be different near the mass than farther from the mass. The clocks are not going to be synchronized any longer. They're going to run a bit slower near the mass than farther from the mass. And then if we have another mass, for example, the Earth, if you imagine this being the sun, if you imagine the Earth coming from far away and seeing the sun in there, it's not the gravitational attraction, that instantaneous attraction, what makes the Earth go in an orbit around the sun. It's the curvature of space-time. So gravity is explained because the masses deform the grid, and the other masses move following the grid, the space-time grid. Now, that also means that when the masses are moving, the grid is changing. So this theory had a lot of consequences, like the light does not travel in a straight line. It bends when it goes through a mass like the sun. That was the first prediction that was verified. The other prediction that he himself, Einstein, made in 1916 is that when you have two masses, like these two black holes dancing a tango, moving around each other, then they are generating waves. Now, these are not like water waves that you see the water going up and down. These are waves of space-time. It's the distances themselves that are changing. They're getting longer and shorter, longer and shorter. Times are also changing. So these are waves of space-time. They're not traveling in anything. They are waves of the grid. When he put the numbers in there, however, he said, this is ridiculously small. He didn't use that word, but he said, this effect is negligible. So the point was that there was no point in trying to measure it. There was no way that he imagined technology to measure it. He was probably using sources, terrestrial sources, but even when we think about astrophysical sources that have much larger masses and they move much faster, they still produce very, very weak gravitational waves. But over the years, we know that there are some sources that we had a chance of detecting with technology that was developed only in the 70s and 80s and 90s. This is a story that took 100 years. For example, we know that some stars explode in supernovae, and some of those supernovae end up with a very compact core. In fact, that at the center there will be a neutron star or a black hole left, and that kind of core collapse supernova would produce like a shock wave. So it would be not a smooth gravitational wave, but it would be a gravitational wave that travels from the source. We know that the stars that are left at the center, black holes not, because they are perfectly spherical. The sources have to have some asymmetry. Perfect spheres do not produce gravitational waves. But if we have a neutron star, which is not perfectly spherical, and it is rotating, then it would produce a continuous gravitational wave. So that's continuous, it's smooth, it's periodic. Maybe we have a chance to detect that. We know that in the very early universe, there were gravitational waves. That's what our theories say. Those are kind of noisy signals. They are very, very small. They are larger at very low frequencies. Those are probably the ones that are most difficult to detect. The ones that we have detected, and those were from the beginning the best sources, were binary systems. If we have two stars, and if these stars are compact, like neutron stars of black holes, then by the end of this dance, they are going to be moving very, very fast because they are small. They can get very close. They can move very, very fast. Like those black holes were moving at half the speed of light when they were about to coalesce. Those could generate gravitational waves that might be measurable. Now, let me put numbers to tell you why Einstein didn't believe that this was measurable. Like I said, the sources of gravitational waves are binary systems, which are the ones that we detected. Those black holes produced distortions of space, of distances, of a part in 10 to the 21. The amplitude of gravitational waves is measured in a fractional change in distance. The longer the distance, the longer the change. The fractional change is the same. Now, a part in 10 to the 21 means that if you're measuring the distance between the Earth and the Sun, that distance changed by about an atomic diameter. How can you measure that? It was very difficult, right? But we knew these things existed. We knew about gravitational waves because, like I told you, if we have two stars orbiting around each other, then they will produce these waves and they will get closer and closer to each other. And some stars, like neutron stars, emit radio waves, like this beam that we see in here. We detect these in radio telescopes here on Earth, and then from the timing of those radio signals, we can tell that if there is a binary system, the binary system is getting closer and closer together. Now, we saw this, we didn't see the merger, but in the 70s, there was the first binary pulsar system detected by Hulse and Taylor. Taylor was the PhD advisor of Roger Hulse. And I like to imagine Roger Hulse, I've never heard that from him, but I like to imagine him doing very, very boring job of looking at these timing signals, looking for some tiny deviations that indicated the binary system, and they found it. And that was the first binary system of neutron stars ever detected, but they were so close, they were orbiting around each other once every 8 hours, that if they followed it over the years, which Taylor did, they saw them getting closer together, just like the theory predicted. So Einstein's prediction that gravitational waves carried energy away from the system and made the stars getting closer together was known. It was actually recognized with a Nobel Prize in 1993. So neither I nor most scientists had any doubt that gravitational waves existed. But we wanted to measure them, not to prove that gravitational waves existed, but to know, to learn about the sources of the gravitational waves, to do astronomy with that. Now, how can you measure something so small? We use an interferometer. In an interferometer, you have a laser beam that splits in two, and then the beam travels. The beam is a wave. It's a laser light. It's a wave, electromagnetic wave. It travels to a mirror far from the center, and then the waves come back. And then when this wave bounces on the beam splitter and this beam is transmitted and they get out, if these two distances are the same, the waves cancel each other at the output, and we have no light. But if these distances change, because, for example, there's a gravitational wave going through, or because the mirrors are being moved by seismic noise, then the waves will not cancel anymore. So if we put a photodiode in here, and there is a gravitational wave, we can see more light, less light, more light, less light, and that's a signature of a gravitational wave. Of course, if there is no gravitational wave, it's not like we don't see anything. We always see something in there because the mirrors are moving a little bit, because the laser beam is fluctuating. There are noises in there. And we have to make the noise of the detectors smaller than a part in 10 to the 21. So it was very, very difficult. But in the 70s, Ray Weiss at MIT and then Kip Thorne at Caltech came up with the idea that if you build this long enough and you use technology, that better technology that was there, you could do this. And they convinced the National Science Foundation, that is all of you as taxpayers, to pay for these 2 observatories, one in LIGO in Livingston, Louisiana, the other in Hanford, Washington, one in the desert, the other in a logging forest. And these are 4 kilometers long on the side. That's 2.5 miles. That's a very, very long baseline. But remember, a part in 10 to the 21 makes the change in distance very small. So small that it's certainly less than an atomic diameter, because that was the change that you would expect if you had the distance between the Earth and the Sun, and these are only 4 kilometers. So it was less than an atomic diameter, less than a proton diameter. The sensitivity we needed was a part in 1,000 of a proton diameter. But that was done. The interferometers were built, and they were built in the 90s, and in the 2000s, we had noise that was about of that amplitude. So we had achieved what the promise, but that was not enough to discover gravitational waves. We needed to do better because the signals were that big. We needed the noise to be smaller. So in 2008, there was advanced LIGO built. And this was not just happening in the US. LIGO Hanford and LIGO Livingston are the only 2 observatories in the US. But in Europe, there are 2, a shorter one, 600 meters long, that's called GEO 600 in Germany, and the 3-kilometer one, very similar to LIGO, that's another European project called Virgo. More recently, in Japan, there's a Kagra detector being built that's also 3 kilometers long, but underground. And in India, there has been approved an observatory 4 kilometers, just like the LIGO one. That's why it's called LIGO India. So this is a worldwide enterprise. And in the 2000s until 2010, we had these 4 observatories working together and not detecting gravitational waves, which was not a surprise. But the idea, and that was the idea from the beginning, was that there was going to be better technology to be installed in the same facility. These are very expensive facilities because these lasers are traveling in vacuum. This is a vacuum system that is 4 kilometers long on each side, on each of the 2 observatories. But we changed the hardware in these detectors. And these might look just like pictures to you, but this is an engineering marvel. And it took hundreds of people working decades to put this all together. And we're still doing that, actually. We haven't yet finished the job. But we have the laser light traveling in a vacuum tube that's 1.2 meters in diameter with a concrete enclosure to protect it from the weather, from bullets, from fire, and we've had all of that. And we had cars crashing into this enclosure. That was in Hanford. The mirrors are not just mirrors bolted to an optical table. These are big mirrors, 40-kilogram heavies, 40 centimeters in diameter, that are hanging from glass fibers from another glass, from another mass, hanging from blades, hanging from blades. Each stage of this pendulum provides some isolation from the motion of the suspension point. And you might have seen this, although you may not remember this, but a pendulum is a very good seismic isolator for some frequencies. You might remember that if you hung a little ball from a string, and this is something that Ray Wise did in the announcement of the first gravitational wave, and you move the suspension point very slowly, then the mass will just follow, will move with the same amplitude. If you move the suspension point at just the right frequency, that's called the resonance frequency, then this mass is going to move a lot. We are going to amplify the motion. That's the resonance. But if the suspension point is moving very fast, this mass is moving a lot less. So hanging a mass from a string is diminishing the motion if the suspension point is moving at frequencies higher than this resonance frequency. So that's what we do with the pendulum, but we do it in 4 stages to amplify that isolation. And that's not enough. We need to hang that from a seismic isolation platform that has several layers. We measure the displacement between the layers, and we cancel it by pushing in the different layers. We have to push on the mirrors so that the interference of the beams getting out of the detector is destructive. We need a coating, a polishing and coating of the mirrors that is cutting edge, so cutting edge that even the manufacturing industries that made the mirrors could not measure how good they were. We could measure that when we installed them in our detectors. And all of these contraptions are hanging from big beams that are hydraulic beams with which we need to cancel the earth tides, and all of that is in vacuum chambers. This takes years to put together. It takes decades to design. But we did it. It was approved in 2008, and by 2015, we were ready to begin seeing something. Now, what was the something that we expected? These are, again, those 2 black holes, but this is now a simulation, a computer simulation of what the space-time near the black holes is going to be. And you see that the distance, this means that the distances here are getting very different. Those are how we represent black holes. And this is how the distances are changing far from the black holes, for example, here on Earth. So we expect to see a sine wave that grows in amplitude, in frequency, until the coalescence time, when the 2 horizons touch. That's a coalescence. That's when one black hole is formed. And then we see that sine wave damping down. Now, these simulations could not be done 25 years ago. They could only be done 15 years ago, 10, 15 years ago. This is also relatively new technology, new advances in the understanding of Einstein's theory put into the computers. And I have to tell you that this was a complete surprise. This looks very simple, right? This did not look simple. This coalescence looked very complicated. So we had been expecting that these computer simulations, in fact, there are some drawings, hand drawings that we did. We knew this beginning. We knew that at the end there was going to be some damping. But in the middle, we drew crazy waveforms. We thought that it was going to be a mess in there, and we needed the computers to tell us how messy that was. It wasn't messy at all. It was very clean. That was actually good because it makes it easy to look these signals in the noisy detector signal that we have. So 100 years, almost 100 years after Einstein published his theory of relativity, when we were just beginning to get data with the detectors, the advanced LIGO detectors that had not even now achieved the sensitivity that we want, we saw this. Let me tell you what this is. I mean, this signal makes me still smile and cry at the same time. This, the blue trace you see in here is this photodiode signal, this light at the LIGO Livingston Observatory. So you see more light, less light, more light, less light, and then you see something that looks like a sine wave. Here, this looks like noise. This is what we always see in there. But here, you see a sine wave that grows in amplitude and frequency. Notice the amplitude. This is the change in distance of these 4 kilometers divided by 4 kilometers. It was a part in 10 to the minus 21 at the peak. But the amazing thing was that when we looked at the photodiode in Hanford, and that is the orange trace, we saw the same thing. Up to the noise, right? This is noise, that is noise, but here, where the signal is bigger than the noise, we saw the same thing. These detectors are 3,000 kilometers away. And you see these photodiodes measuring more light, less light, telling you that distances and times are changing in the same way in these two very, very distant detectors. And they are not doing it at exactly the same time. At Livingston, we are very proud because the signal arrived in Livingston 7 milliseconds before than Hanford. So here we are showing the two signals shifted by 7 milliseconds. Notice the time in here. The time is very short. This is a very short signal. And that's how we knew from the time, from the frequency of these waves and the frequency at which they stop, we knew that these were big black holes. They looked just like the numerical simulation, and we could test that with not just by eye. We don't have graduate students looking at this time trace all the time to say, oh, there's a wave. We do this on the computer, but this is a beautiful picture. So this is what we like to show, but this is not how we find it. We are more sophisticated than this. But this was amazing. This was the first detection of gravitational waves, and we weren't even expecting it. We were about to take data for a few months, saying, well, we'll test data analysis techniques. Virgo was not ready yet, so it was the two LIGO detectors. We probably won't see anything, but we'll take data for 3 months and see what's there. Even before we began taking data 24/7, this surprised us. So it took us a few months to get convinced that this was not a drill, this was not a joke, this was not a hack. It was difficult to prove that this was not a hack. That was actually the most difficult test. It was not lightning. It turns out that we found in our investigations that within a few seconds, the largest ever recorded lightning happened in Burkina Faso. It took a day or two to prove to ourselves that that lightning could not have produced this signal. But that's how far we had to look. We had to prove this beyond any reasonable doubt. I like law and order, so So on February 11, 2016, that detection was on September 14, 2015. A few months later, in February 11, we were ready to say, we did it. We did this in a press conference in Washington, and actually, we chose that date because we had only just finished all the tests and the article that we sent for refereeing in January, so we were doing things very tight. But this was just the availability of the speakers and the people attending. But that turned out to be a very special day, too, because it was the first day that the International Day of Women and Girls in Science, determined by UNESCO, was celebrated. And it was very nice because the person presiding the press conference was Franz Cordova, a woman scientist, an astronomer who was presiding, who is directing the NSF and was presiding the press conference. There was Dave Wrightsey, too, the executive director of the LIGO laboratory, Ray Wise and Kip Thorne, later recognized last year with a Nobel Prize, and myself as spokesperson of the collaboration. and it was an amazing day. I don't know how many of you heard the news that day. How many of you? Did you remember that day? About half of you. It actually had an amazing reaction from the public that we did not quite expect. These are two of my favorite examples. A few days later, only days later, a gravity dress appeared. We had nothing to do with that. But that's our waveform. I have the dress. It doesn't look as nice on me. But I have the dress. There was an ad in subways and billboards in New York City saying that scientists found gravitational waves in outer space. If only it were that easy to find storage space, walk-in closet. This is an ad for storage space. That tells you that this was known everywhere, and we were so proud of sharing this. Now, the we that we talked about was the LIGO scientific collaboration and the Virgo collaboration, because we had been working together during the initial era. We worked together here, even though the Virgo detector was not running for this time because they were still building it. We worked as a team. Teamwork had a lot to do with the success. We are now more than 100 different institutions in 15 different countries. LSU is one of those institutions. Caltech and MIT are the two involved in the LIGO laboratory. But there are 100 different institutions from many different countries. There are young people, senior people, physicists, engineers, technicians, everybody working together. But what I like to imagine when you see that, it's not institutions, it's not Einstein working at any one of those institutions, not even the Nobel Prize winners. We were very happy last year in 2017 when Ray Weiss, Kip Thorne, and Barry Barish, who was the executive director of the LIGO laboratory that put initial LIGO and advanced LIGO on the map, were recognized for the observation of gravitational waves, that first observation, but their affiliations were listed in the Nobel Foundation press release as the LIGO-Virgo collaboration. This was all a recognition of teamwork. But this is a team. It started with Einstein. People in the early times doing the first experiments for gravitational wave detection was Joe Weber in University of Maryland, Kip Thorne and Ray Weiss, Peter Solson, my advisor. I love that picture. These are my two mentors. These are the two people who really formed me, Ray Weiss and Peter Solson. But these are the people who do this. It's young people. It's energetic people. We are changing all the time. We are brainstorming all the time. And that's what you need to do this. The picture I like the best is my group on that February 11. And you can see I was far. I was in Washington. They were in Livingston. But we were all very happy all across the globe. Let's go back to the science. I told you September 14, 2015, that was the first detection. We were just beginning to take data for a few months. In October, we saw something that looked like a signal, but it wasn't so clear. We kept taking data. On December 26th, although it was still December 25th, this is UTC time, but it was still Christmas evening here in the US, we saw another signal. Another signal from smaller black holes. These were almost 30 solar masses each. These were 8 and 14 solar masses. If the black holes are smaller, then the coalescence frequency is a bit higher, so this system spends more time in our band. The first signal was a fraction of a second long. This signal was about a second long. And I want to make you listen to it. How many of you have listened to this chirp before? Let me test you. Let's see if this is what you heard. I'll make you listen to the long signal first. Oh. volume. Okay. That's a short one. That's not what you heard. This is what you heard. This is a cheat. We cheated a bit. We added 400 hertz. The signal that you saw is in the 100 hertz regime. It's like a C note. It's very low. It's like a thump. So we didn't like that very much. So we learned from astronomers. They paint ultraviolet light, infrared light, X-rays in beautiful blues and red and yellow. So we added 400 hertz. And that's what you hear. But now you know the truth. So we had this first observing run. We had these two detections. We measured the sensitivity of our detectors to the distance to which we can detect binary neutron stars. We took some time down to improve the sensitivity. We want this number to be close to 200. This number was close to 20 megaparsecs in initial LIGO. We want to be 10 times better. In November of 2016, we began taking data again with better sensitivity at Livingston especially. And we were waiting Virgo to join us. They were very hardly getting their detector together to join this run. Why do we want 3 detectors? Because with 3 detectors, you can triangulate. Not only you can see more signal, you can know more about the signal, but you can triangulate. With 2 detectors, not so much. You can kind of tell the astronomers, look there to see if you see something. But with 3 detectors, that's when you can do better science. So we began taking data in November 2016. It was January of 2017 when we saw another merger of black holes. We were excited about that. In June, we saw another. We were not so excited anymore. But then Virgo joins August 1st. We needed to go down August 25th. So there wasn't a lot of time to take data together. We said, well, this is going to be a test. We are going to have simulated signals. We are going to see how it is to analyze data from 3 detectors together. But on August 14, we detected another black hole coalescence. And even though this was the 5th of black hole coalescences, this was very special because now with 3 detectors, we could localize it. And we did. And we pointed astronomers there, and they didn't see anything. Actually, they haven't seen any convincing counterpart. There are some discussions, but there's nothing really definite about electromagnetic counterparts of these black hole detections. But you don't expect any, because black holes are black. They don't emit any light. So you don't expect to see any light. We still look, everybody looks, but it's not a surprise that nothing has been seen. So we were ready. I mean, this run had been a success. On August 17, only 3 days after that, we saw another signal. And this was very special for many different reasons. But one of the reasons that was very special is that the signal that we saw was very long, which meant that the masses were very small. So small that these were probably not neutron stars, not black holes. These were probably neutron stars. And when neutron stars coalesce, they do produce light. And we had some supporting evidence of that because the Fermi satellite is a satellite that is looking at the sky for gamma rays almost all the time. So a relatively weak gamma ray burst, a signal in gamma rays, only 2 seconds after we saw this one. And now you know that we like to convert things to sound. We didn't have to cheat in here, except that we don't play the actual detector signal. We only play the waveform because the masses are smaller, they are smaller than the noise, so you cannot hear it so clearly, but you can hear the waveform. And this is what it sounds like. So this is our signal, that's Fermi data. This system, according to our measurements, was about 130 million light years away. And after traveling 130 million years, these two signals, the gravitational wave signals to the LIGO detectors and the gamma rays, arrived with only 2-second difference. That proves that these two signals were traveling together. 1 second in 130 million years. Now that was not all. Because Virgo was there, we could localize. This was a localization from the gamma ray signal. This was our localization from the triangulation with the 3 detectors. So we could tell the astronomers, not look there. We would have done this only with LIGO, all this arc. We could tell them, look there. And this was relatively close. In astronomy, 130 million light years, it's nothing. So they could say, oh, these are the galaxies in there. We'll see whether anything changed in those galaxies. And there was one galaxy, NGC 4993, not a nice name I would have chosen for a galaxy, but that's, again, astronomy. And then that galaxy did not have anything there before. And at this time, this day, it had a bright spot. There was a bright spot that was not there before, and it was fading. This is actually the signal published by LCO, Las Cumbres Observatory, who looked at this signal, and I like this comparison a lot nicer. It's a lot nicer. But of course, we had to put this into sound. We did. NASA, being NASA, had to put this into a movie. So this, I think, it's the best movie of the night. The theory is that we had these 2 neutron stars orbiting around each other, getting close, emitting gravitational waves, coalescing, emitting these gamma waves in the direction, and then all kinds of electromagnetic waves in all directions. And that's what we and astronomers saw. For the gravitational wave detections, we had published papers that have 1,000 authors. For this detection, we published a paper with astronomers, with all the astronomy groups that followed this, with 3,600 authors. That is teamwork. Now, this was announced again in a press conference in October 16 last year, so we are getting very close. 100-year story, and I think I'm almost done. And again, I want to show you how to imagine scientists. You don't need to imagine physicists or astronomers as Einsteins. We are normal people. Some of these people are very young. There is Andy Howell here, your own from LCO and UCSB. But again, Franz Cordova presiding, and we had here people from LIGO and Virgo and Fermi, and then here astronomers from many different collaborations and many different projects, all working together. This is the image of scientists that you should keep in your head when you tell people, when you want to imagine, when you tell people to imagine a scientist, not an Einstein. So now we have a lot of data. We know a lot more about black holes. We know about this one merger of neutron stars. These are the neutron stars that we know from radio signals. These are the black holes that we know from X-ray signals. And now we are adding another sense. We like to say that this is multi-messenger astronomy. I like to say that we added the sound to the movies. It's like when the movies became talkies. I think that's what they were called at the time. Now, the discovery of this neutron star merger, it was not announced in the press and it was not talked about as the discovery of gravitational waves, not even as multi-messenger astronomy. This was the discovery of gold. Why would you say that? Why would they say that? Cosmic alchemy, that's one of the, that was one of the headlines. That's because in astronomy, it had been for a long time a mystery where the elements come from. You might have heard that we are all made of stardust. Yeah. Have you heard that? Yes. That's because when you look at the elements on the periodic table that we learn in school, of course, there are some elements that are man-made. Actually, we make elements that are heavier and heavier and heavier. But there are lots of elements, not just here on Earth, but we can see the evidence of these elements in the sun and other stars that are heavy elements, heavier than iron. And it turns out that I'm not an astronomer, but I've read the papers, and this is what they tell me, that stars, when they have nuclear fusion, they produce heavier and heavier elements until iron. Iron is very stable, so it's not easy to produce elements heavier than iron. So we are all made of stardust up to iron. After that, like gold and platinum, that was more difficult to explain. And the explanation that there was is that these were produced in supernova explosions when elements were moving very fast, colliding with each other, and then forming heavier elements. But it turned out that there doesn't seem to be enough supernova explosions to explain all the gold and heavier elements that are seen. So the other theory for how these elements were produced is that they were also produced in collision of neutron stars. But nobody had seen one until now. So we have discovered gold. The calculations say that this merger of neutron star produced not just a kilogram, not just a few pounds, not just a ton of gold. It produced about 100 Earths worth of gold. And another amount, similar amount in platinum, and another similar amount in all the other heavy elements that we don't use in jewelry. So that adds to the explanation of where the elements come from. Most of these elements come from exploding massive stars and white dwarfs, but these heavier elements come from merging neutron stars and supernovae. So now you know where gold comes from. And this was actually one of the best evidence and one of the best ways to prove this theory right and wrong is something that was done here at Las Cumbres Observatories because it was following the emission, what is called the light curve, the brightness of the signal, that bright spot near the galaxy versus time. It followed. And it can do that because it has several observatories around the world, so you don't have to interrupt the observations at night, at daytime. Because if it is daytime here, it's nighttime there, and then you begin observing there, and then you begin observing there. So you can have many different points during the whole day, and that's what they did. And the fact that there is this rise, this was the only project that saw that rise for this event. So that's the advantage of an observatory like this one. So with that, let me finish telling you about the future. We are now down. We are going to be up. We are increasing the sensitivity of our detectors to see a bit farther. We're going to begin taking data again in about February for about a year. We will see more black holes. We are hoping to see more neutron stars. How many? We don't know, but we hope to see at least a few. We'll see. That will tell us how often these things happen out there. Nobody knew about black holes until we saw them, and now we can measure the rate of coalescence of black holes. So we are learning a lot about astronomy, and we will be doing that. But then we need to increase the sensitivity of the detector. So we will be doing in this cycle of up and down, a year improving the sensitivity, a year taking data for about the next decade or two. That will give us a lot better understanding of signals that have periods of milliseconds. So those are these stellar mass black holes, or small black holes, astronomers like to call them, and neutron stars. I think that we will have a few surprises too, but those are difficult to predict, of course. But there are lots of other gravitational waves other colors of gravitational waves, if you want, that are produced by other sources, like the massive black holes at the center of the galaxies. Those are much lower frequencies. You need a space detector to measure those. And that's in the works. The European Space Agency has approved this for a launch in 2034. So we'll have to be patient. But we need to work on that now to make it happen in 2034. That's how long these things take. We can see supermassive black holes, coalescence of supermassive black holes, or perhaps a stochastic background produced in the early universe. And we can do that using these neutron stars, the radio signals from the neutron star, as if they were an interferometer of galactic scale. Now, talk about long. This is 4 kilometers. This is 1,000,000 kilometers. This is now measured in parsecs. It's a galactic interferometer. But we can do that, and people are doing that. And my prediction is that the next gravitational waves, well, we are going to keep the next different gravitational wave is going to come from these pulsar timing experiments. And of course, there is the early universe. That's a much more difficult thing to detect, but there are lots of experiments trying to do that by measuring the polarization of the cosmic microwave background. And that's a mouthful, but you will hear about that in the papers when it happens. And that is all coming to you. The future gravitational waves had to wait 100 years since Einstein to be detected, but they are here, and we'll keep detecting them for the rest of your lives, my life, and this is the beginning of gravitational wave astronomy, and it's very, very exciting. Thank you.
Anyone have any questions?
I measured success of talks in numbers of questions, so I'm beginning to be disappointed.
On the periodic table, there were 2 elements that didn't appear to be shaded, any of the colors?
They're man-made. Technetium and neon.
Which ones?
61 are man-made.
Oh, yes, and this one. I don't know about that. Maybe somebody else in the audience knows.
They're man-made.
They're man-made, that's right. Yes, that's right.
Technetium and Fraser.
And I think there's a few more that are not in here that are man-made.
So now, more or less, we have 3 LIGOs. Are there plans for any more? Any other country planning to do one?
Yes, I mentioned that, well, there are 2 LIGOs, and there's Virgo in Europe. Those are the 3 operational now. The next one that's going to be operational, and we hope we're going to begin taking data with them in 2019, is Kagra in Japan. So this is a 3-kilometer underground cryogenic detector in Japan. That's the next one to come online. After that, in the 2020s, we'll have this one in India. But now we are beginning to think about 3rd-generation detectors, about detectors that are longer, perhaps 40 kilometers long, or 10 kilometers long, but underground. Those are going to be new facilities, and they probably won't be built for another 30 or 40 years if we begin thinking about those now. That's why I'm saying that this field has decades of evolution still ahead.
You should talk to Elon Musk. He knows how to drill tunnels.
I'd love to do that, yes.
What's the wavelength of the laser you use in LIGO?
We use an infrared laser produced by an indium YAG laser. It's 1 micron, 1064 nanometers wavelength.
Wouldn't the sensitivity of your instrument depend on the ratio of 1 micron to 4 kilometers?
Well, actually, that's a good question. At some point, it was thought that, yes, if you're using your wavelength as a ruler, that's not quite what we do, but in principle, if you think of the wavelength as a ruler, then if you make the wavelength smaller, then you might make your detector more sensitive. It turns out that our sensitivity depends a lot more, not so much on the wavelength, but on how powerful the laser can be, how stable in frequency, how stable in amplitude. And the solid-state lasers, in the very beginning, in the 80s, people were thinking about gas lasers. My first experiments with prototypes were with an argon ion laser, a green laser. That was the initial design. And then solid-state lasers came along that had a longer wavelength, but were much, much more stable. And that's what we went for. We might change the wavelength again in the future if it's convenient, but it won't be because of the wavelength. It will be for the power and stability of the laser.
So you're actually able to measure a small fraction of a wavelength.
Yes, a part in 10 to the 10. Yes.
You talked about the consortium of so many people coming together to do this incredible project. Can you talk a little bit about the leadership that was able to herd all these cats into one place to do that?
Well, there are several parts to this. The initial and most critical part is the LIGO laboratory. That is the Caltech and MIT, the team at Caltech and MIT that got the grant from the money from the National Science Foundation to build the two observatories in Livingston and Hanford. They have about 160 people now. The collaboration has 1,000 people. Actually, I think 1,100 last time I looked. So the collaboration is a much, much wider team because these are the people who develop the technology, analyze the data, calibrate the data. There's a lot of things to do. So it's not just Caltech and MIT. In the US, there are lots of other groups like mine at LSU. We have independent funding, and then we have agreements with each other, and that's a LIGO collaboration. So the LIGO laboratory has an executive director who manages the money of this big project in the US. But then there are a lot of other principal investigators in the US and lots of other investigators in other countries with their own funding. And we all have agreements that are not financial. They are just honor agreements, handshaking, although we do write these down. And that's the collaboration. The leadership of the collaboration is a democratic collaboration. We have elections every 2 years. We've always had more than one candidate running and that's because we actually encourage people to run so that we discuss the future of the collaboration. And these discussions are always very civil, very constructive. But we have elections every 2 years. The first spokesperson was Ray Wise. The second one was Peter Solson from Syracuse University. The third one was Dave Wrightsey from University of Florida. Then it was me. And now it is David Shoemaker from MIT. So this rotates. It's always been from the US, but I suspect that won't always be the case. I don't know if that answers your question, but that's as close as I can get.
I'm trying to think of how this is done. I'm a retired civil engineer. What type of engineer designs LIGOs? Mechanical, electrical?
All of those. We have optical engineers, mechanical engineers, vacuum engineers. What do they leave out? Civil engineers too. Civil engineers. Although civil engineers were hired at the beginning to do the civil construction, they are not on staff because they were hired in the beginning. So now it's maintenance, which is not easy, but there are no civil engineers on staff. Yeah, that's true. We have all the other kind of engineers on staff. But it is, again, teamwork.
Any idea, since you've been involved a long time, what the total investment has been made in capital to accomplish this fantastic?
It's difficult to calculate, but NSF calculated this since the original funding that was proposed in 89 and granted, I think, in 92. So since 1992 until now, it's been a bit more than $1 billion.
That's nothing.
Well,
Either this or one even longer.
Okay, let's thank Gabby again. We have some refreshments outside. We invite you to stay around and talk with her a little bit more. Thank you for coming.
I'll be happy to answer more questions.
Thank you.